Hello everyone. So now in the last lecture we have talked about rotations of a tetrahedron. We have presented permutation groups, symmetric groups, alternative groups, even and odd permutation. Every permutation is a product of disjoint cycles. Every permutation can be written as a product of transpositions. Even number of transpositions can even okay. And then we have presented the table for A4 alternative group of order 4 on 4 elements, and then we have given a figure which this group actually defines the rotations of of a tetrahedron. Okay, we have drawn those figures, and then let me show you. This is the reference from a book which also um, so you can see these are the rotations of a regular tetrahedron. Now I'm going to talk about an example, like few applications. Okay, so let me say something in this box. So many molecules with chemical formula of the form AB4, such as methane CH4 and carbon tet- tetrachloride CCI4, have A4 as their symmetry group. I should write it blue. AB4, such as methane, which is CH4, and carbon carbon tetrachloride, which is CCI4, have alternative group of order 4 is their symmetry group. Symmetry group. Now this is the figure. This figure is the tetrahedral AB4 molecule. This figure shows, and you can see this. It has the symmetries. It has the similar symmetries like this regular tetrahedron have the rotations of this regular tetrahedron. Okay, so when all these molecules have some kind of this kind of a shape, which has a A4 alternative group of on 4 elements, is a symmetry group. Okay, now many games and puzzles can also be analyzed using permutations. So let's try an example which talks about it. So we name it example 11, which is encryption using a permutation. Okay, so an interesting application of permutation is cryptography. Cryptography is the study of methods to make and break secret codes. So let me just write that. Cryptography study of methods to make and break secret codes. Right. Now, the process of coding information to prevent unauthorized use is called encryption. Historically, encryption was used primarily for military and diplomatic transmissions. Today, encryption is essential for securing electronic transactions of all kinds. Cryptography is what allows you to have a website safely receive your credit card number. Cryptographic schemes prevent hackers from charging calls to your cell phone account. Among the first known crypto systems is the Caesar cipher, used by Julius Caesar to send messages to his troops. Caesar encrypted a message by replacing each letter with the letter three positions further in the alphabet with XYZ, wrapping around to ABC. Now, identifying the 26 letters of alphabet with 0 to 25 numbers in order, the Caesar method replaces the letter I with the letter I plus 3 mod 26. Now, for example, the message A T T A C K A T D A W N Dawn is encrypted encrypted is D W W D, should write on the next line, D W W D F N D W G D Z Q. Okay. To decrypt the message, one replaces the letter I with the letter I minus 3 mod 26. So to decrypt the message, one replaces replaces letter I with I minus 3 mod 26. Okay. Now, any permutation can be used as a cipher. To use a permutation, say alpha, which is 1 goes to 3, 2 goes to 4, 3 goes to 2, and 4 goes to 1. To encrypt the message attack at dawn, we first now to encrypt the message given above, attack at dawn, We first break the message up into blocks of 4 letters, each ignoring the spaces between the words to obtain a plain text. Plain text. So message will be A T T A C K A T D A W N. Now this has the added advantage of disguising the letters, the length of each word, which makes breaking the code more difficult. When the when then reorder, we then reorder the 4 letters in each block in the same way alpha reorders the integers 1, 2, 3, 4. So let's write that. Uh, so we then reorder the 4 letters in each block in each block in the same way alpha reorder the permutation, reorder the integers actually 1, 2, 3, and 4. That is, the first letter is to put at third position, the second letter is to put at, so that is, so we have now how many? 12 positions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Now the first letter, alpha sends 1 to 3. So the first letter is A. We send A to third position. So that is A. Then the second letter goes to 4. So then the second letter is T. It goes to 4. So it goes to 4. Then then the third letter goes to 2. Third letter is T. So it goes to 2. And then fourth letter goes to 1, which is again A. Right? Similarly, we do to the to that to the second block. So first letter goes to third position. Let us see here. Second letter goes to fourth position. Third letter goes to second position. And final. Similarly, first letter goes to third position. Second letter goes to fourth position. Third letter goes to second position, and fourth one goes to third position. That is how we use encryption to write this message, and particularly this alpha, using this alpha. Okay. Then, of course, one decrypts a message encrypted by alpha by using alpha inverse. So now one decrypts the message encrypted by alpha by using alpha by using alpha inverse. To enhance security, one would use a permutation of long length n and blocks of length other than n, so that anyone not authorized to receive this to receive the encrypted message would not know the permutation length. In cases where the number of message characteristics is not divisible by the block length, the sender simply fills out the last block with nonsense letters. For example, for the message retreat at dusk with block length 4, we could use RETREATATUTDUSKIUE. The recipient of the message will recognize the nonsense letters as padding needed to complete the last block. So, Enigma machines were cipher devices used by Germans in World War II, 1939 to 1945. An Enigma machine had 3 to 5 wheels that would scramble the letters of a message. The machines were easy to use and offered a high degree of security when used properly. Although messages encoded with Enigma machines were difficult to break, operator negligence and the capture of number of Enigma machines and the tables of wheels setting by the Allied forces allowed Polish and British cryptologists to break the code. Okay, so this is how we use the permutations to encrypt the messages. Perfect. Now let's talk about another one. You can actually name it, that is Rubik's cube. Now the Rubik's cube made from 48 cubes called facets is the quintessential example of group theory puzzle. It was invented in 1974 by the Hungarian Euro Rubik. By 2009, more than 350 million Rubik's cubes had been sold. The current record time for solving it is under 7 seconds, or maybe less than that at this time, and under 31 seconds blindfolded. Although it was proved in 1995 that there was a starting configuration that required at least 20 moves to solve, it was not until 2010 that it was determined that every cube could be solved in at most 20 moves. This computer calculation utilized about 35 CPU years denoted, donate, donated by Google to complete. In early discussions about the minimum number of moves to solve the cube in the worst possible case, someone called it God's number, and the same stuck. And the name stuck. A history of the quest to find God's number is given at the website. Like the website is, I can write it. Okay, maybe there is dot or there may not be. To set of all configurations, the set of all configurations of the Rubik cube from a group of permutations of order, you can't write it. So let's say the set of all configuration of the Rubik's cube form a group of permutations of order 43 252 003 274 8 489 489 856,000,000, probably in trillions or more than trillions. This order can be computed using GAP by GAP. I'm actually preparing new lecture series. GAP is a programming language where you do group theory and abstract algebra and everything like that. So you can actually learn that. I'll try to upload those lectures in few weeks. This order can be computed using GAP by labeling the faces of the cube as shown here. So let's label the faces. Let's make two tables. Okay, and then right. So then what can we do is it's 9, 12. Let's label those faces. 10. This is left direction. 15 and 11, 13, 16. Then we have 17, 18, 19, 20, 22. This front. 21, 23, 24. Let's write 1 on the top, 2, 3. This is top. This is 4, 5, 6, 7, 8. The bottom. Okay, let's first complete the sides. So this is going to be 25, 26, 27, 28. This is right side. This is 20 and 29, 30, 31, 32. And then we have 33, 34, 35, 36. This is rear. This is 37, 38, 39, 40. And then we can label the downside 41, 42, 43, and then 44, bottom, and 45, 46, 47, and 48. Right? Perfect. Remember, each cube inside a Rubik's cube is a cube, actually. Yeah, that sound delusional, but it is. The group of permutations of the cube is generated by the following rotations of 6 layers. It's gonna be the lots of them. So I'm gonna just make you. Yeah. So these are the permutations of the cube, which is the the permutations by which the permutation group of the cube is generated by. Okay, you can see there is every kind of permutation, and we can actually put these permutations in GAPE, and we can get a group which is generated by them. And if you check the order for that, that is going to be the one we have mentioned here. That's going to be the order. That's going to be the order of the group. Perfect. Thank you so much. That's all for this lecture.